So next, we go to some. I want to give you some intuition rather than requiring you to understand difficult mathematics. So you will see a lot of mathematical equations in the slide, but you don't need to worry about that if you cannot trace all the details of these equations. I want you to get the intuition, and in an engineering approach, I think this is what I require in this course. If you have used WRF, you will heard about finite difference method. But for unstructured mesh, I want you to meet a new friend. Hello, finite volume method. So if you are using rectangular grid and you are living in a Cartesian coordinate system, then you will be happy to handle all the things in X direction and Y direction. So this is your familiar thing. But for MPAS now, it is a global model. So basically, you have to handle the curved surface on the sphere that the Earth actually idealized to. The Earth is actually not a perfect sphere, but for our purpose, and treating it as a perfect square is more than okay in our case. So in the curved spherical geometry, you have the spherical mesh, and then this mesh is unstructured, so that add to some complication that you may not be comfortable with. So I have to introduce the coordinate system that we will be using will not be XYZ. We will use a zonal direction for any local point on the surface on the Earth, which means the west to east direction. And then the other direction is the meridional direction, which is along the south and east direction. So we are talking about a local point. So if the local point changes to another location, actually the direction changed when you look from the space, but it's okay. So and for the vertical direction, they are the same. We still use a Z direction, meaning pointing upward or going radially outward from the center of the Earth. And then actually, I talked too much about the horizontal topology of the unstructured mesh. In the real model, the model needs to take care of the vertical dimensions. And as you see, there is vertical layers, and it is actually using some formulation of vertical coordinate. And I think you don't need to worry about that in this course. It is too difficult. So let the engineered product, which is the atmospheric program, the software, which is well done, let it handle the vertical stuff for you. Okay, the next slide. For each cell, we have to put the variables of the atmospheric state to a cell. Some variables are scalar, like temperature and the density of the air, and temperature, and then scalar, and then mixing ratio of the moisture, something like that. They are scalar variables. But for wind is actually vector variables. So when we discretize the space in the cell, we want to put the wind to the face of the finite volume. In rectangular grid, we often call it the C grid staggering, because there has been A grid and B grid, which puts the wind vector somewhere else. So here in this figure, like the black dot, which is actually means at the center of this three-dimensional cell, pressure, temperature, and RT, maybe it is mixing ratio or some variables representing the amount of moisture is represented as at the center of the cell. So actually within the cell, temperature and pressure have some little variations within the cell. Usually we take the average among the volume of the cell and then represent it as a number at the center of the cell. And here, U, the solar wind, will be represented as this hollow circle points here on the face, on the lateral face of the cell, and also here on this lateral face of the cell, of the cell. And for V, which is vertical wind, we put it on this face and then the face behind. And for vertical wind, denoted by W, it is put on the upper face and the lower face. Okay, this is what C-grid staggering is in rectangular grid. Now we go to unstructured grid. When we draw unstructured grid, we are so lazy that we often only draw a horizontal drawing for the horizontal cell in this way. Now the red arrow represents a wind vector. We will put the wind vector at the center of the face. And this figure is three-dimensional, and to represent the vertical wind, you see that the wind vector is put to the upper face and the lower face. So comparing the rectangular grid and this unstructured grid, they actually share the common principle that scalar are put to cell center and wind is put on cell face. This has the attributes I will introduce in the next several slides. Now a few jargons on mathematical things. In these complicated equations, actually the spatial operators that occurred the highest number of times is the green one. The green one have this, somebody called the del operator, and then the dot operator together. It is actually called divergence operator. And I will introduce flux a moment later. And there are some terms that have the del operator directly add on something. It is called the gradient operator, the red one. And then there is also some cross operator here, meaning cross products of vectors, and usually it represents something which is turning, something spiral, something like that. And it is encircled in blue. So in the following, I will only introduce the divergence operator, and then we will don't worry about the other one. They are too tedious to explain. Okay. The next slide, I would like to introduce the divergence theorem. Mathematically, the formula is like this, but if you think of it in the figure, it is not difficult. You know, calculus is actually something from the first principle. You have the limit if you learn about it in higher mathematics. Limit something approach something, then it becomes calculus. Here, it is actually, we want to have, in the time equation, it is actually a length of time. In the calculation, we actually have a finite delta t, which is a time step. But if in the limit state, the time step becomes very small, the delta t approach 0, we will write about infinitesimal time step, and then the derivative will become run something, run t. This is the differential representation of something. In Also in the spatial operators, there is a discretization of a space. We put the continuous atmosphere into discretized cells. And here you see in the spatial dimension, we are having grid spacing, delta X, delta Y, or delta C, something like that. So the differential representation of the relationship is also the limit that such grid spacing become infinitesimally small, and then the derivative along this three-dimensional space become this del operator. It is just a representation in the calculus language. Now we go back to our program that use finite volume. So this is the finite volume. It has some phase. So what the divergence is? Divergence means now you have wind, which are vector, and in the arrangements of the grid, we have already put the vector on the face of the finite volume. And usually we use the direction facing outward, which we usually call the normal direction of the face, and denote it as a vector n pointing outward. So what is flux is that when there is wind blowing out of the finite volume, the flux is basically the amount of air going out of that phase. So if we use an averaged wind vector in our program, like where the mouse is. So also in reality, the wind is also have a small variation in this area. We also take average and use just one vector or one number to represent the average wind on this phase. So the flux is basically this wind vector times the area of the phase. So this will be proportional to the amount of air going out of this phase. So you will want to mention air is compressible, or we in the model we allow air to go in and out of this final volume. So what is the total amount of air going out of this final volume? This is called flux going out of this final volume. And in mathematical notation, you will see something like this, surface integral of something, blah, blah, blah. So it actually means the flux of airflow going out of this final volume. Okay. And as you know, if air really go out, then the density will become smaller because in the same volume, there is fewer air mass. So you go back to the equations. This kind of equation like this one, it's actually say that this is the flux of air mass going out of a cell. It is related to the rate of change of density when you want to simulate what go later to the next time step. Okay, you already understand this difficult equation. So for other variables, they are very similar. For heat, we talk about the heat flux. So if this cell is warmer, and then the warm air mass goes out of this finite volume, you will have heat flux. So the rate of change of temperature or potential temperature is related to the heat flux going out. Of course, you have driving terms like if there's aerosol in this final volume and there is sunshine, actually the aerosol may absorb some solar energy. So this is the so-called driving term that will take in the effect of radiation to the potential temperature of this of the air in this finite volume. So you understand this equation also. For moisture, this is similar. There is moisture flux. If the cell has more moisture than its surrounding, there may be a net flux of moisture going out of the volume. So, and if you consider the rate of change of mixing ratio of moisture in this finite volume, you will see that the rate of change of moisture is related to the minus the outgoing flux. And also you will have some driving terms. As I said before, moisture is classified into different states like vapor and cloud water and cloud ice. Say, if within this finite volume, there is condensation, meaning that some moisture in vapor state change to cloud state, then this is the driving term for the QV, for the vapor, the driving term will be negative. There will be fewer vapor in this finite volume. And for QC, which is the moisture in cloud stage, there will be a positive source term or driving term. That means the condensation process is happening. So this is the equation about moisture. And for wind, it is a little bit more complicated. There is a Coriolis term, and also there is a pressure gradient term that I will not go into details here. So these are the intuitions behind this seemingly complicated coupled set of partial differential equations. Go ahead. This is taken from Stu's book also, General Circulation. You must have already learned about this. Take this A case. If there is horizontal convergence near the lower surface, like there's some area, the wind is blowing to this central region from this direction and also this direction, then we call it a convergence in near the lower surface, and the result will be air is squeezed to go up, right? And then as air squeezes go up, it will have the consequence in the upper part of the tropopause in just the opposite way. So consider what our numerical weather simulation will do in its dynamical core. So you imagine this three-dimensional cell is now here at the center of the convergence. So we calculate the flux. Now the wind is blowing inside, so it is there is a net flow of wind or air into this finite volume here. And the consequence is that, as you know, air is compressible and pressure can change. So this is handled by the coupling of these set of equations. You see, the right-hand side actually for wind is related to pressure and also other variables. So they can affect each other. And these variables actually can act like constraints of each other variables partial differential equations, and they coordinate themselves. So there is a scalar variable representing pressure for the center of the cell here. So when you carry out numerical simulation of this set of coupled finite differential equations, the calculations will result in the pressure variable will increase because the flux, the horizontal flux, is going into the cell, and then air is compressed, and then P is increased. But as the divergence theorem see, if the upper and lower phase is freer to move, then the flux go in from horizontal phases, but the flux will go out from the upper phase, and then the pressure will not build up. When pressure try to increase, this couples equation will result in the W, the horizontal wind will increase. So in this numerical simulation of the atmosphere, that will result in increase in vertical wind, which is in correspondence to the intuition of this common situation that when convergence occurs near the surface, the air will squeeze to go up. Okay. So take the next case B, when there is heating, say the surface is warmer on the land surface, and then it will affect the lower layers of the atmospheric model. So that's the way the source and sink term add. Here, if the land heats up the layer of air it is adjacent to, there will be a source term, a positive temperature change, or we can say it is a heat flux from the land, from the soil to the atmosphere. So this is positive. So in the equation, it will tend to give a positive rate of change of the potential temperature. So the air here will heat up. And then in the coupling of the equation, this will lead to the density will change, and then the pressure will change. The result will be pressure will be become smaller, but it will expand, and then it tends to go up. This equation will result in also increase in the vertical wind velocity, W, here in the cell. So these two examples will give you intuition on how the time integration of this set of coupled partial differential equation is actually simulating what's happening to the atmosphere, as far as the model can be constructed to best model the physical processes. So the next slide. This is from the MPAS tutorial. It says the same thing. Firstly, it is mentioning the transport equation in conservative form, mathematical language. Okay, it is a partial differential equation relating to the derivative with respect to time to the spatial operator. And then MPAS is using the finite volume formulation. So it say if you integrate over the cell, okay, integration operator, something like that. And then you apply the divergence theorem that relate the volume integral to the surface integral. You will arrive at the formulation in the discretized way, discretized in time and space. So this is the finite time step delta t, and this is finite, not represented yet, finite discretization of the space. And then we can use a computer program to implement the calculation of these finite equations.